Hello, we're here today to talk about creating value in paste operation processes. My name is Tim Stewart, and I'll be walking you through the presentation today. So let's start with a performance comparison between the ideal situation and potential current situation. The hypothetical that we'll walk through throughout the presentation is a 10-station paste assembly operation. The ideal performance is that all 10 stations are perfectly balanced. There's no variation in production. There's no waste produced, and very high quality. Reality sometimes looks a bit different than that, though. So some of our operations may be longer due to wasted motion than they are in an ideal situation. We may have a dead time on average due to variance within that operation. We may also have dead time due to poor balancing. And let's see what all of those mean. From a current performance perspective, we have operations not balanced, wasted motion, variation causing stops, and also defects. And we're losing a lot of efficiency because of these different problems. So when we look at why wasted motion may be causing dead time, we can look at this on a step-by-step basis, even within an operation, and perform an ergonomic analysis using video that can detect unnecessary or wasted motions within that standard work. So this is the best operator doing these tasks. And what we see is that currently the operation takes X amount of time. But if we look at each of these steps from an ergonomic perspective using the video, we can find where people are performing redundant tasks, reaching where they don't have to, how the ergonomics of the workstation could potentially be rearranged, and come up with a much more optimized flow for those different operation steps within a given station. And what that will do is it will reduce that overall amount of time that that station takes, or that operation, and generate some savings. Next, we'll look at the dead time that's created due to the variance within the operation itself. And when we look at process variability, it's very often the hidden source of inefficiency in paste operations. And that can be caused by a lack of adherence to standard work. It could be caused by tasks that are difficult to perform, by variations in the material feeds, any number of different things. But the effects of variability within that station are going to be poor quality, lost time at that individual station, where setting the operation time less than the takt in order to be able to accomplish it most of the time, and even more lost time when the operation is done quickly. And I'll show you what I mean by that in a minute. From a line stoppage perspective, when the operation takes longer than the takt, the entire line is forced to stop until this operation is complete. So let's take a look at this in a little bit more detail. Let's say that our normal takt time is 55 seconds for one cycle. We may have to set the average operation time to 50 seconds because we know that there's some amount of variation. And so if we set a target of 50 seconds, that way most of the time, even with some variation, we'll be able to get it done in less than takt time. But now let's say that we have this amount of variation in how long that process or that step actually takes to complete. In that case, what we're going to see is that 90 or 10% of the time we're going to get done in faster than 30 seconds. And when we do that, that creates 25 seconds of wasted time where the operator is going to stand there idle waiting for the next cycle to happen. On the flip side of that, in the 90th percentile operation time based on the process variation here, it's going to take 70 seconds to complete that task. And when it takes 70 seconds, not only are you kind of wasting time at that operation, but you're also stopping the rest of the line for 15 seconds. And that time is wasted across every single station among those 10. And so there are ramifications to having that process variation in there that, you know, if you have this kind of a situation happening at all 10 spots along the line, you're never really going to have a takt time that actually happens in the takt time. You're going to be stopping very, very frequently. And so you may not have this much variation relative to the gap between your operation time and your takt time, but any amount of variation is going to cause you to have all of these different inefficiencies. So the solution is to continuously capture information about the process to identify all of the different sources of variation within there, and then to either mitigate or eliminate them. Next, we'll look at the dead time due to poor balancing. And again, we're looking at our 10 operations here, and we see that the amount of time that those operations take varies anywhere from 30 seconds to 70 seconds. And there's 500 total seconds of work along that line. And your lines may not be this unbalanced, but having the video will allow you to see how much time each cycle actually takes along that manual assembly line. And so then, if we get those operations in balance so that we take some of we shift some of the operation steps themselves so that we now have 50 seconds at each individual station, what that allows us to do is up here, we're averaging about 70 seconds per cycle with 51 pieces produced per hour. Here, we're averaging 50 seconds per cycle, and without any more resources in the production line, we're able to get 40% more production at 72 pieces per hour. Now, you may not be in a position where you can sell that many additional products. You may be producing at the speed with which your customers will consume them. So in that case, what you can do is, by condensing this down to 7 operation steps from 10, you can get some kind of efficiencies in there where you don't have operators starting and stopping quite as often, and you have more, at one individual station. And so you can drop from 500 seconds down to 490. Not a whole lot, but just getting some of those efficiencies from combining operations. And then the 70 seconds of work per operation, now you can look at this and be able to complete the same amount of work that you were up here at 70 seconds per cycle. So still 70 seconds per cycle, same number of pieces, but you can reduce your labor and the associated resources that you have along the line to support each worker by 30%. And so significant savings available just by balancing the line and by looking at the ergonomics within the station and looking at the individual operation steps, and then also by reducing the variation within the process. Now, one other question that I've been asked is, are these one-time savings or annual savings? And some of the customers that I've talked to have argued that once you make that improvement, unless you make another improvement in year 2, that was just a one-time savings. And I'd like to take a second to kind of shift the mindset about that, because let's say that our baseline performance coming into the project is that 50 units of production, or 50K per week. And during the project, we take 4 weeks to implement the solution. We see consistent gain in production, across those weeks, and at week 4 or 5 of the project, we're up to 70 pieces produced per hour. And so we've seen performance increases through the implementation, and now in week 6, week 7, week 8, week 9, even assuming that we don't get any additional gains from the software, what we've done is we've set a new baseline of performance from 50 up to 70. And that's now our steady state performance after the implementation. So we've seen an efficiency gain of 40% during that time, and it keeps going. It doesn't stop after this particular week. And when we look at this on a monthly basis, it's the same thing. So on a monthly basis, let's say that we're getting 500 units per whatever time period out of production, and that's our baseline going into the implementation. And again, we have kind of a 1 month plus implementation, and we get to 700 pieces. So again, a 40% gain, and that performance carries through the implementation. So now in months 5, 6, 7, 8, 9, 10, etc., we still see that performance gain from our original baseline to our new baseline performance. And that again keeps going. So additional months. So then, if we look at this on an annual basis, once again, we've had an established baseline of performance once we come into the project. But now, through the implementation, we're getting that 40% improvement, and there's no reason why that 40% improvement would go away. Just as we saw with the weekly and the monthly, it's not that it resets back down to 500. We don't lose those performance gains. And so with that established baseline, it keeps going. We see that 40% gain, and you still have in year 2, year 3, year 4, year 5, that performance gain, that efficiency gain against your original baseline. And so it is an annual savings and not a one-time. So with that, I hope that that helps. And if you have questions, please reach out to me. My name is Tim Stewart. My company is Visual Decisions, and you can reach me at tim@visualdecisions.com at any time. Thank you.